Welcome back to ECE 340. Not much time left. Your final is 3 weeks from tomorrow, and we only have 5 more class meetings. And in that time frame, we will try to squeeze 2 more homeworks and a final exam into that remaining time period between now and final exam. And please note that the final exam is on a Wednesday. Even though we are meeting on Tuesdays and Thursdays, make sure you're arranging your schedule to be available on Wednesday, the 8th of May from 1 p.m. until 3 p.m. The time is a little different. It's shifted 30 minutes start time from when we normally start. What I want to be able to do in these last few times that we meet is cover essentially a transition or a bridge from Fourier series into Fourier transforms, and then talk about sampling. What does it mean if you need to sample at the Nyquist frequency? What happens if you don't sample that fast? You start to see things that you shouldn't be seeing, things called aliases. And so now we need to talk about, or hopefully understand a little bit of that and see how you might be able to determine what frequencies are present in a signal when you sample it at a given frequency or at a particular rate. Today what I want to do is actually start partway through chapter 7, which is the Fourier transform chapter, discussing distortion. You're now in a position to understand or talk about distortion, and we'll address 2, amplitude distortion and phase distortion. Amplitude distortion we can hear more easily than we can hear phase distortion, but yet we can see phase distortion much more readily than we can see amplitude distortion. That's discussed or talked about more thoroughly on page 720, or starting on page 720 of your textbook. But we'll see if we all start to understand what it means to have a distortionless system that you're transferring information through. We'll then continue a little bit in chapter 6 with Parseval's theorem for periodic waveforms, which really just means that the signal power in one domain hasn't changed when we switch into the other domain. Frequency domain and time domain, if we look at the power in the signal, it better be the same in both domains. But given the formula that we will determine or derive in the frequency domain way of computing the power in your waveform, we can actually get maybe more useful information. And you've already applied that. When I ask on exam 3, what's the power in a particular frequency interval or band? And you could simply look at the spectral lines in that frequency band and determine your power in that frequency interval. That's what we'll talk about here with the use of the frequency domain power expression. Then we will get more closely connected with the Fourier transform by an example. Excuse me. The example is going to start manipulating or adjusting a given waveform, its period, its pulse width, and then how does that period and pulse width influence the line spectra? How does the time domain adjustment of a waveform impact the frequency domain information or the frequency domain picture? And that will hopefully lead us into a little bit of an intuition into what's happening with the Fourier transform. Where were we going to start? We were going to start in the first part of chapter 7, or the mid part of chapter 7, jump back into chapter 6, and then start working our way up to chapter 7, which is this last topic. Try not to get lost. What do we want to now start with? Distortion. And this is distortion with respect to signals and not money or anything else. So this is oh, that wasn't funny, was it? Huh? So we now have amplitude distortion and phase distortion. Those are the two that we will investigate. Here's the idea. Suppose I give you a signal, call that the input signal, and for this class, typically we refer to that as x, but x now is made up of two frequencies, 2 cosine 10 pi t plus 4 cosine of 20 pi t. What we want to do is actually inject that signal input, x of t, into different systems. So I'll subscript that system by an I. We will see what generates or what comes out of that system at the output, and then I want you to be able to tell me, given this input and the resulting output, was that system causing distortion? And if it was causing distortion, was that distortion amplitude distortion? Was it phase distortion? Or was it both? Or was it neither? Here's the first output. Suppose now that we say output number 1 from system 1, let's say y sub 1 of t is 4 cosine of 10 pi t minus 5 pi plus 8 cosine of 20 pi t, and I'm running out of room, but I guess I have a wide piece of paper, minus 10 pi. Since you guys are good at tests, I'll give you a quiz. And in particular, I'm going to ask you two things. Whoops, it's maybe not enough room, but is this system introducing amplitude distortion given this input x and this output y? And is it giving phase distortion or producing phase distortion? There's the input signal x. Here is, let's say, system sub 1. System 1's output y sub 1. How many people, by a show of hands, think that this is experiencing amplitude distortion? How many am I counting? 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to say anything. I can't give you the answer. So I said 8 said yes. How many say no? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're not doing the wave if you came in late. And I think we actually have more than 20 in the class, so some of you aren't participating in this election. You're abstaining. That's okay, I guess, but I'd really like for you to commit one way or the other. I'm not going to hold you to this, and I'm not remembering who's voting what, whether you're red or blue. Go Wildcats. All right. We've determined amplitude distortion, yes or no. Phase distortion, yes or no. How many people think there is phase distortion in this system? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. How many do not believe there is phase distortion? 1, 2. All right, we got a little bit more participation. We increased the participation rate. We now have 4 more people participating. What's the answer? There is no distortion in y sub 1 of t. What? All right, let's figure out what that means. If we go back to this x and y sub 1, we could have a scaling or an adjustment, up or down, smaller or bigger, in terms of amplification. If we look at the first frequency component, 10 pi, omega equals 10 pi radians per second, looks like it was increased by a factor of 2, from 2 to 4. We go to the next frequency component, 20, it goes from 4, and if it amplified by 2 also, which means if everything's amplitude by the same amount, there is no amplitude distortion. 4 to 8, that's a factor of 2. The amplitude is adjusted consistently to get in both terms. Okay? Could have had a V8. I'll just give you a V8 next time, and it'll be less painful. All right, so there is no amplitude distortion because the amplitude in all components by a factor of 2. Does everybody see that? Why we can claim that there was no amplitude distortion between x and y sub 1. Now, let's see what happens with the phase. If we look at the phase, what we really want is we want each component to be shifted by the exact same amount of time. And if you recall how I wrote y, I had not factored out t in either of these arguments, so maybe it wasn't easy to tell what the time delay was in each of the component parts. But and that's what I want to do now. Let's factor out a common multiple or factor, or basically factor out this omega from both terms, and then I'll have t minus some time delay. And if that time delay is the same for both frequencies, then there is no phase distortion. The phase then, if we looked at the first frequency, omega 1 equals 10 pi, then we had for its argument, it was now this 10 pi t minus 5 pi. There's the omega 1. And if we factor that out, we now have 10 pi t minus 1/2. If we do the same thing for the second frequency, which was 20 pi, we had 20 pi t minus 10 pi. That now, if we factor out the 20 pi from that factor, we have 10 minus 1/2. And we can hopefully see that this delay in both arguments is the same. Each component, each frequency was shifted the same amount of time. Is that clear? And if that's the case, then you do not have phase distortion. The original phase or argument might appear like, oh, wait a minute, the angles are different in the two frequencies. Yes, they are, but hopefully they are varying linearly with frequency. And that's what you want in a system. You want a system to adjust the amplitude consistently across all frequencies to maintain no distortion in the amplitude, and you want it to produce a linear phase shift. So your phase curve should vary for your system linearly to not produce phase distortion. Meaning, in a distortionless system, you want the following picture. If you inject x of t, an input, into some system, you want the output, y of t, to simply be some gain constant k times the original x. And the original x, it's allowed to have some time delay. Then you're not distorting the signal. Now, let's see if we have learned what these mean. Suppose now I give you a second system, system sub 2, and I say it generates the following output. Y sub 2 of t is 4 cosine of 10 pi t minus 5 pi plus 7 cosine 20 pi t minus 10 pi. And remember what we had to begin with. We had an x that looked like this. First thing you want to do is, do you have a linear system? A linear system is going to preserve the frequencies. If you have nonlinearities, then you might get 3 times the frequency content in your output, the frequency value in the output that you had in the input. Because if you had a squaring behavior, a nonlinear action, now you're going to get a doubling of a frequency component in your output versus your input. Memorize x of t, 2 and 4, 10 and 20. Coming out of the second system, this is now what we experience or measure. And I want you to answer, is there amplitude distortion and is there phase distortion? Is there amplitude distortion? Yes, because we would expect, if we just use the first component as our case, it's now experiencing a gain of 2. The second component is not experiencing a gain of 2. It's experiencing a gain of 7 over 4, not quite 2. This now is telling us then that 7 is saying that we have amplitude distortion coming out of that system. What about the phase? Do we have phase distortion? If we go back and remember what we had in y sub 1, this is exactly the same argument in both cosines, and those had the same delay. So there is no phase distortion in this signal. Both components experience the same amount of delay. One more, since this is so fun. Y sub 3 of t. Let's say that you now have 4 cosine of 10 pi t minus 5 pi plus 7 cosine 20 pi t minus 5 pi. Well, if you believe that the last one had amplitude distortion, we haven't changed anything in the amplitudes between y sub 2 and y sub 3. Y sub 3 is also going to give us amplitude distortion. What about the phase? That, with respect to 20 pi t, that should have been minus 10 pi to produce the same amount of time delay, which allows us to conclude then that this particular system sub 3, is producing both amplitude distortion and phase distortion. Questions on distortion? That should be a gift on the final if I give you such a question on distortion. Does this system have amplitude distortion or phase distortion? I hope it's now clear how to analyze such a question or problem. Let's move on now to back into chapter 6 and talk about periodic waveforms. In particular, let's pick up Parseval's theorem, because we're going to have this theorem, Parseval, in both chapter 6 and chapter 7, but chapter 6 is periodic waveforms. Chapter 7 is aperiodic. They don't repeat. They're just sort of one-time events. And those waveforms are then energy signals. So we'll have Parseval's theorem for energy signals, but now we have periodic waveforms and we have to worry about their average behavior and their average power. Parseval's theorem for periodic waveforms. What Parseval allows us to do is actually relate the two different domains. This is now going to allow us to relate the power in both the time domain and the frequency domain. So we're going to relate the time domain power to the frequency domain power. If I said on the final exam, produce a formula or an expression for the average power of a waveform x of t, could you do that? What would be your formula for, let's say, p average, the power in a periodic waveform? Well, let's say you can identify the period. Let's simplify things. I don't want to mess with limits. So now let's just assume that we have a periodic waveform and we can explicitly identify the period. We can measure that. We know the period. What's the formula? Is it simplified? Meaning, if I give you a complex waveform, x of t, on the final, you should be able to find its magnitude, square it, integrate over one period, divide that time interval out, and you have the average value of that waveform, the average power in that waveform. This is a time domain formula. And I hope you feel comfortable with that. You're basically just squaring a signal, and we generalize this. X could be a current, it could be a voltage. We just generically say that's a power, even though you guys know that you need something flowing through or something measured across a resistor maybe to talk about power. We just sort of assume that we've got this in one ohm resistor. Just sort of understood. Is that okay? So we can generalize this and just say, okay, this is our power formula. Now, what we want to do is derive the average power in terms of the frequency domain description that we know exists for periodic waveforms. If I give you a periodic waveform, I just lobbed you a periodic waveform in various ways, I guess with one sport or the other. Maybe I could pass you one. Now you have or throw you one, hit you with a strike. You have a periodic waveform. Now what do you know you can do with that waveform? You can find its Fourier series. Let's do that. Here is what we want to do. Well, before we do that, we sort of need to remember another way of writing the absolute value of something squared. This is why you studied Chapter B to begin with. We're not going to change the period that we're integrating or dividing out or integrating over, but we can now rewrite the absolute value or the magnitude of x squared as x times its complex conjugate. That's exactly the same as the magnitude squared. Hopefully that's not an issue. How did we write, or how did we synthesize x in terms of the exponential Fourier, the complex exponential Fourier series? Do you remember what the formula was without your cheat sheet? Maybe you have your cheat sheet embedded on your forehead, right? Or in your forehead. There, I'll get that part. You were combining things, weren't you? And what were you combining? You were combining sines and cosines, but in the complex exponential, you're writing sines and cosines as these phasors, rotating phasors. And you have to scale each of those complex phasors by an amplitude or a complex number, and we called that, let's say, capital D with a subscript for the different harmonics. Let's say that we now are summing from n equal minus infinity to infinity of capital D sub n e to the j in omega naught t. Hope that sort of looks consistent with what you're used to seeing. This is now what we could use to replace x of t, but actually we're going to be selective with what we do and don't replace in that integral for the average power. Let's find the complex conjugate of that. So I'll give you, you can take that home and come back and you can have an infinite number of terms conjugated. All right, it's not that hard, is it? But, I mean, effectively, that's what we're doing. We could now say this is now the sum from minus infinity to infinity of the complex conjugate of each of those coefficients, d sub n star, and then we conjugate that phasor so that it's now spinning in the other direction. If the first one was counterclockwise, now we're spinning clockwise in the complex conjugate of x, little x of t. Is anybody wondering why we can do that? Is it clear? Let's just convince ourselves. Now that you're able, you should just have fun with this. You wake up Saturday morning and you go, you know what? I'm going to prove to myself that this is correct. You have the skills to do it, right? Or maybe you can't sleep and you wake up and you go, let me just derive this result. Had too much caffeine before I went to bed tonight or something. Maybe. All right, so let's say that we have the following product of two complex numbers. We have a complex exponential and we have a rectangular form of a complex number, and we want to conjugate it. And you could just realize that we, for this u, are consolidating all of those three different terms. And this piece right here is really what we're calling d sub n in the earlier result. Well, the complex conjugate of a product is the product of the conjugates. So that this now says that, oh, we can now say a plus jb conjugate, or d sub n star e to the ju star. And we know how to conjugate the rectangular and complex exponential form of those. We can now say this is a minus jb, and this is e to the minus ju. And this then should make us feel a little bit more comfortable with the replacement that we did earlier. When we had x star, little x of t star, or conjugated, that now gives rise to this. All right, now we can use it. Let's now return to our formula or our expression for the average power. That's 1 over the period, integral over 1 period, x of t, x star of t, where the star is the complex conjugate. Now what I want to do is replace that time domain conjugate of x with its frequency domain representation. And we just wrote that down. We now have 1 over t naught, integral over 1 period, x of t, and now let's replace x star of t with what we said we were okay using. That's now this infinite sum d sub n star e to the minus j n omega naught t dt, where this is just the complex conjugate of our time domain waveform x. So we're allowing x to be complex, little x. Now we get to play with sliding things in and out, or interchanging limit or integrals and summations. Let's pull the summation outside the integral. That will allow us now to do the following. Now we can say that this is 1 over t, well, actually let me push that 1 over t naught. Let me let that accompany the integral sign as I slide things back and forth. And I will have now this summation from n equal minus infinity to infinity. This d sub n star is not a function of time. And because of that, I can slide it outside that integral. That integral, I'm integrating out time. You just pull that capital D sub n. That's just this complex number that weights these sines and cosines. And if you wanted to know, oh, what's the weighting at the fourth harmonic? Then you're looking for capital D sub 4, aren't you? And that's going to be 4 times omega naught, the frequency that that coefficient is associated with. And it not only has capital D sub 4, but you also have to worry about capital D sub minus 4. You need to take them in pairs. The negative and the positive come together so that you end up with real quantities. We can now put together what's left. We have 1 over t naught integral over t naught. The x of t stays inside the integral. Then we have an e to the minus j n omega naught t dt. And that should look very familiar to us, this expression. What was this? This is actually the formula we use to find those complex exponential coefficients. We multiplied our x times e to the minus j n omega naught t. We divided out the period, and that gave us our capital D sub n for whatever n we were interested in finding. This is now in the blue curly braces. That's capital D sub n. And that's just the analysis. If you perform this, this is telling you how much frequency content is at that particular frequency in omega naught. Question?
Could you also use 1 with all the everything that isn't natural
I'm not quite sure what you're asking, but this is the way I want to derive it. Because now I'm going to have capital D sub n star times D sub n. And we know what happens when we multiply something times its conjugate. Now allows us to do the following. We now have the following expression. We have this summation from minus infinity to infinity of D sub n star, and everything else on the right-hand side is just D sub n. But that can be rewritten as simply the magnitude of those coefficients squared. And that's now the expression for the frequency domain's power in a waveform x, little x. And that now allows us to basically equate that final expression with the original expression for the power. And that's called Parseval's theorem. Parseval's theorem now says let's just equate the time domain and the frequency domain powers. The time domain power was right there. And the frequency domain power is there. This is now our time domain power expression, and the right-hand side is an equivalent power expression. It's just using the notation that we've used in the frequency domain. Meaning we can now say that the average power in x of t, and x of t is periodic by assumption in this argument, that average power equals the sum of the powers squared powers in the complex phasor components of its Fourier series. Questions on that? Let's look at an example just to convince ourselves, and it's nice when you're first beginning to maybe crawl, right? Instead of going out and running or sprinting, a lot of times it's nice to not injure yourself and do something that you kind of know what's going to happen. We'll just say we're going to crawl. What if we now found the average power of, let's say, x of t equaling 5 cosine of 60 pi t. Now, this example I said we were going to crawl because hopefully you know the answer in the back of the book. If I give you a sinusoid, you know what the average power is relative to that sinusoidal description. How do you find the average power? Or what's the shortcut formula that you should maybe know by this point in the semester? The amplitude squared over 2. In this case, that's 5 squared over 2 or 12.5 watts. Let's now just prove that to ourselves, both ways. If we now look to verify that, in essence, where did that expression come from is what we're deriving now. P average was just 1 over the period, integral over a period of a cosine omega naught t dt, and we need to square that expression in general. Now we have, if we square that integrand and factor the amplitude out, we have a squared over t naught, integral over t naught, and now we have cosine squared omega naught t. But this is why you have all of those formulas memorized in chapter B, right? Cosine squared is 1/2 plus 1/2 cosine of 2 omega naught t. And what happens when we integrate cosine of twice the frequency over one fundamental period interval? Have 0, don't we? We have the same positive area as negative area. This now disappears when it goes through the integral, and we end up with now a squared over t naught, 1/2 t from 0 to t naught. The upper limit's the only interesting limit that we have in that evaluation, and the t naughts cancel, and we end up with the formula that you had already memorized, a squared over 2. What happened to omega naught? If I changed omega naught, is our formula going to change? Hopefully from this derivation you can see that it's independent of the frequency. All you need are the amplitudes. Our average power does not depend on the frequency. In this case, if we were curious in terms of, oh, what were you integrating over in terms of a time length? Omega naught was 60 pi. Now I'm getting hungry thinking of 60 pi. That's 2 pi f naught. Didn't have enough for lunch before class. That's a pretty common occurrence. F naught is now 30 hertz. And that allows us then to say, if we were actually integrating that, if we were interested in it, we would have been integrating over a pretty small interval. Of course, that's pretty large when we're talking about the frequencies in electrical and computer engineering, but now that's, in this particular example, 1/30th of a second. And how many harmonics did we have in little x of t? We just had the fundamental, didn't we? We didn't have any higher harmonics. We just had cosine of 60 pi t. We just had one harmonic. So if I said draw the line spectra, the complex exponential line spectra, which I didn't ask on the exam, but some of you gave me that instead of the compact trigonometric form. I think you got to going too fast and didn't read the answer or the question slowly enough. It's about the same, isn't it? Now you have to do the negative frequencies and the positive frequencies. But what kind of a picture are you going to see if you drew the line spectra for little x of t? You're going to have one line in the positive omega and one line in the negative omega, and you know where those omegas are, don't you? They're at 60 pi and minus 60 pi. All right, so let's now look at computing the frequency domain power. we're going to do this in the long way. By that I mean we're going to actually find the amplitude or the coefficient in the complex exponential expansion the long way. We're going to compute it from the formula. What's the formula for the first harmonic or the fundamental? Capital D sub 1. The average value of a cosine is A sub 0 or D sub 0. If we don't have any DC offset, plus or minus, it's 0. So we don't have to worry about capital D sub 0. Capital D sub 1 is 1 over T sub 0 integral of over T sub 0 of x of t. And now what do we do? What was our strategy for computing these coefficients? We scale that x of t by what? Sines and cosines, right? A rotating phasor. This complex exponential. E to the minus j in omega naught t. Can I squeeze all of that in here? I now have e to the minus j. Little n is 1. Omega naught is 60 pi t dt. And now you need to go back and recall how to integrate cosines and complex exponentials. Well, an easy way is let's just go find Euler. Let's use Euler and rewrite this complex exponential in terms of sines and cosines because they're at the same frequency. That's the way I'm going to do it. Pardon? The comment was, wouldn't it be easier to rewrite cosine in terms of complex exponentials? A or B? B or A? It shouldn't matter. It's really whatever you feel comfortable with. So if that's what you feel comfortable with, that's what you should do. Today what I want to do is go the other way. I'm going to say cosine, and now I'm going to make E into Euler. So that now I have this 1 over T naught integral over 1 period of 5 cosine of 60 pi t, and now I'm going to replace that complex exponential with cosine 60 pi t minus j sine 60 pi t, and I get to cheat by expanding my paper. And now maybe you can see why I did this. Now it's going to look consistent with what I had before in the time domain. Now I'm going to have a cosine squared. I now have a 1 over T naught integral over T naught. I have two terms. I have a 5 times cosine squared of 60 pi t. Then I have a minus j5 times cosine 60 pi t sine 60 pi t dt. Now I need to go back to my elementary school trigonometry class and remember this expression. Cosine A sine A is sine 2A, right? Or 2 sine of 2A. So this is now 1/2 sine of 2A, where A was 60 pi. So that's now 1/2 sine of just the red piece. I still have that 5 if I need to keep track of. But what happens when I integrate a sinusoid twice the frequency over 1 period, fundamental period? That gives me my 0 again. this piece, when integrated over that interval, is going to give me 0. The only thing I have left then is this 5 cosine squared, and we've already done that. That's now this 1 over t naught, integral t naught 5, and we can rewrite the cosine squared as 1/2 plus 1/2 cosine of 2a. Again, we can allow this second piece to vanish because we're integrating it over one fundamental period. And we're left with now 1 over t naught, integral over t naught of 1/2 dt. Let me put the 5 out front. And I now have 5 over t naught, 1/2 t, and we've done that before, haven't we? So we now have 5 over 2 t naught over t naught, or this d sub 1 is now 5/2. If we want the power in that frequency, 60 pi, we have to include not only this positive subscripted d, we also need to take care of its twin, d sub minus 1. And what is d sub minus 1's relationship to d sub 1? They're just conjugates. And now if I give you 2.5 and say take the conjugate of that, you can pay me as you go out the door on the day of the final, right? You can pay back that gift. That's just the real number again, being returned. Now that you have d sub 1 and d sub minus 1, it should be trivial to sketch the line spectra for little x of t. There's omega, and that could be either in omega or maybe it's in frequency of hertz. If it's in omega, this is now 60 pi, and this is minus 60 pi. It's supposed to be a straight line, and it's supposed to be originating at 60 pi at 5/2, and this is now 5/2. Or in terms of hertz, it's at 30 hertz or minus 30 with an amplitude of 2.5. How did we say to compute the average power in the frequency domain? What was our formula? That was this infinite sum, wasn't it, of d sub n's magnitude squared. But in this case, all the n's go away except for 2, minus 1 and 1. We take d sub minus 1 and square it, and add it to d sub 1 and square it. Doing that, we now have 5/2 squared plus 5/2 squared. And because I know the answer in the back of the book, I can do the math. That should be the same, right? We've now derived our expression, magnitude squared over 2, from the time domain. We've now verified for a single component sinusoid what we could use in the frequency domain description of that result. Questions on that? Yes or no? The question, if you picked that up on the microphone, which I doubt you did, was, do we have to go through this derivation on the exam? And the answer is no. I was trying to convince you that this makes sense. I'm trying to develop your intuition. Now I might give you the following problem. I might say something like, what if you're given this picture? I might now just give you a line spectra and ask you a question. I might say something like, what is the power of, let's just say this is now some new signal, x hat of t, between 100 pi and 200 pi radians per second, where I might give you something that looks like, oh, well, here is, let's say, 60 pi, here's 120 pi, here's 180 pi, here's 240 pi. This is now the frequency axis, omega. This is maybe d sub n. This is now the magnitude of d sub 1, the magnitude of d sub 2, the magnitude of d sub 3. And we have to do its twin or copy in the negative. Whoops. I wanted that to be green also, but you can make yours whatever color you like. These should be the very same height. And as you know with my drawings, they're not always the most consistent. Yes, sir. Yes, the question was, can we just use, I don't want to spend twice infinity, I just want to spend once infinity to compute this. And the answer is yes, as long as you pull out the DC piece. You can't do double the DC. So if you factor out DC, d sub 0, then you have this infinite sum excluding 0, and you can simply double the positive piece and throw away the negative piece. Is that okay? So yes, you can do it that way if you want. Because these lines, if I was drawing it properly, these should all look the same in the positive and negative picture. Meaning if I square this and double it, I'm going to get the same as adding the two that were squared. That's the idea. Now, if I wanted to find the answer to this question, which is the average value between 100 pi and 200 pi, what would we write down? Or do we know how to solve that? What's the first thing we probably want to start doing? I didn't hear that at all, but everybody was excited to give me an answer. Okay, we need to figure out which harmonics are in that interval between 100 pi and 200 pi. Luckily, our frequency axis has been labeled. Here is, let's say, 100 pi, and here is 200 pi. We only have two lines or components between that interval or in that interval, and we can now take those. We can say we now need to make sure that we include the negatives as well as the positives, but we only have the two unique lines. And if we had a DC piece, we would need to include that, but we're not going to double it, are we? It's just going to appear once. Is everybody clear on that? Yes. Now, what we are doing, I'm not sure I quite understand the question, but this is now, we need to go back here and pick up. If I now ask you to give me the power in a certain interval, you have to do it in the positive and the negative side. The earlier comment was, can't we just focus on one side and double the result? And that answer is yes. But if you don't, then you need to make sure that you include the magnitude of d sub minus 3 squared, because that's, I think, what our formula said, wasn't it? That's what this is saying. This is saying iterate on these subscripts and just take each one and square it. And if you add all of those pieces up, you'll find the average power in your x of t. And if you had an infinite number of harmonics, you would need to do that for an infinite number of coefficients. Does that help answer your question? Where did the divide by 2 go? It didn't, well, where did the divide by 2 go? Anybody want to help? What are we doing here? We have to remember that we've been playing with a lot of different representations, different Fourier series. The divide by 2 comes in if we were in the compact trigonometric. We moved into the complex exponential. So the factor of 2 is sort of there with Euler. If you start looking at a cosine and represent that as complex exponentials, you're going to get that factor of 2 built in. It doesn't appear in these complex exponentials. But if you look in the book, I think maybe even in that first table, table 6.1, you will see those factor of 2's in there if you start using Parsevals with compact trigonometric. Okay, so make sure you're clear on which of these coefficients you're using to compute the average power or the power in certain intervals. Does that help answer your question? So it's buried in there implicitly, that power or that factor of 2, because now we're dealing with complex exponentials. And that makes for maybe a cleaner looking formula. We don't have to worry about that factor of 2 in there. If you now had a DC term, what would be the average power between 100 pi and 200 pi? So now if I wanted to low pass, so I'm band pass filtering, aren't I, right now? If I low pass filtered, then I would have to include the DC piece. Meaning if I now did a new problem and I said, why don't you low pass filter and maybe low pass filter out to 100 pi? Now we're doing something out to there, aren't we? And in fact, if we now had a DC piece, it would be right there. And we would need to include that, but we wouldn't double it, would we? It is only one DC. Is that clear? Does that answer your question?
Wouldn't the DC part actually have a 1/2? The others have like a 1/2. That part is clear.
So now whatever you ended up being computing for d sub 0, however you define that, if that was now in terms of some a sub zeros, there's already a built-in factor of 2 built into d sub 0. So to get its power, all you do is square it here. DC. That's all we did in our formula. So all of those factors of 2 are accounted for if we've computed the d's properly. So we don't have to worry about scaling that answer. We just take the amplitude, square it, and add up the pieces of interest. Questions? Now, that's chapter 6. Let's move, well, not quite, I guess. Now I'm trying to straddle or bridge or go from chapter 6 into chapter 7. And here's how I want to do it. Let's look at the following signal, and it's going to be periodic. So we'll have a period to worry about. We'll have a pulse width, and that resulting signal, since it's periodic, will have harmonic content, which we can write or represent as line spectra. We want to now look at how all of these influence each other. If we have a period, I'm going to make the pulse width D, and I'm going to talk about the line spectra. Here's the periodic waveform that I want to discuss. And this is in the time domain. This is now little x of t. And there's my pulse width. It's going to start at 0, and it's going to be on for a length of d. Then it's going to shut off, turn back on every capital T. That's the period of this waveform. D is the width of the pulse, and T is how often it repeats. Now, what I want to do is I want to find its Fourier series. This is a periodic waveform. I should be able to do that. Ooh, those are supposed to all have the same amplitude. Sorry. Those are flat. Maybe I should put that. I think I wanted that to be A. So this is A, and this is A. I'll label it if it doesn't look quite like A. I have an amplitude A pulse of duration little d, and then that repeats every capital T units of time. What I want to do now is play with T and D and see what happens to the line spectra. In order to do that, what I want to do is derive a generic formula for the complex exponential Fourier series coefficients associated with this little x of t. Does everybody understand what we're doing? So our first issue is simply to apply our formula to compute capital D sub n for this periodic waveform. Let's now do that. And if you've forgotten, that's the complex exponential Fourier series is section 3 of chapter 6. Little x of t, what we're saying is we have a periodic waveform, x of t, and we want to write that as an infinite sum of complex exponentials. And they are scaled by capital D sub n. That's formula 29A, and I might refer to this to get us thinking about what we will do in the Fourier transform. This is how we build up x of t out of different frequency pieces. This is just a sine or a cosine, isn't it? This is sines and cosines, and this just tells us how we weight those sines and cosines. That's our weighting. This is then how we would synthesize x of t out of a bunch of harmonic content of sines and cosines. We build it up by adding up all of these sines and cosines. That's the synthesis equation. We now need to find capital D sub n, which is the analysis equation for our x of t. What's the formula for D sub n? We divide out our period. We integrate over a period. We scale x of t by e to the minus j in omega naught t dt. Since that earlier one was the A piece, this is 629b, and this is the analysis equation. If somebody said, how much of the first harmonic do you have in that x of t, you could find it from this formula. How much of the fourth harmonic do you have? Well, you could plug in little n equal to 4 and find it. You could see how this x correlates to that frequency component. What I want you to do between now and Thursday is compute these capital D sub n's for this waveform. You're going to have a decent, well, do you know, before you even compute, do you have a capital D sub 0? Do you have a D sub 0? What is D sub 0? D sub 0 is the average value, isn't it? So now you could get that graphically without going through all of that, right? You just take what's the average value of that pulse over that interval of time t. That's D sub 0, and you could use your formulas and integrals to find that if you want. But that's just going to be A times D divided by T, right? Capital T. Then you need to find D sub n in general. And that's going to be that formula right here, this analysis formula. I want you to do that by Thursday.